Let's work practice problem number 2 on page 251. I'll read the problem. It says, a rifle can shoot a 4.2 gram bullet at a speed of 965 meters per second. Draw work energy bar graphs and free body diagrams for all the parts of this problem. I'm going to skip that. For part B, find the kinetic energy of the bullet as it leaves the rifle. What work is done? C, what work is done in the bullet if it starts from rest? D, if the work is done over a distance of 0.75 meters, what is the average force on the bullet? And E, if the bullet comes to rest by penetrating 1.5 centimeters into metal, what is the magnitude and direction of the force the metal exerts? Again, assume that the force is constant. Okay, so let's go through these one at a time. Let's solve. Well, let's do part B first. I don't really like the bar chart thing, so I'm going to kind of skip that. Well, kinetic energy is 1/2 the mass times the velocity squared. So that's the velocity. So this is how much energy is being carried by that bullet. It's quite a bit. 0.5 times 0.0042 times 965 squared. And you get 1,955.5. We'll call it K equals 1,960 joules if we round it off. Okay, you agree with that? See what did the book get? Yeah, that's right. Now part C. Now, what work did the rifle do on the bullet if the bullet started from rest? Well, where did this bullet get its energy? From the work done on it by the rifle. So, now this all does stem from the work energy theorem. The work done by the net force on the bullet will be equal to the change in kinetic energy. Well, this is K final minus K initial. It says the bullet starts from rest, and this is the work done by the net force that's the rifle, that expanding gas of gunpowder blowing up, applies to the bullet. So that work is just going to be equal to 1,960 joules. That makes sense to everybody? I mean, the bullet has this much energy. What gave it that much energy? The work done by the rifle. Part D. Well, if delta x equals 0.75, well, this is the work equals force times displacement times the cosine of the angle between the force and the displacement. So we know what work was done, so now we just need to solve for delta x. So delta x is equal to the work divided by the, wait, I'm trying to find the force, I'm sorry. We're given delta x. We know that, we know this, and we know this. So force is equal to the work divided by delta x. Now, what is the direction of the displacement? Well, the bullet came out of the rifle to the right. The displacement's to the right. The force is to the right. Everything's to the right. So this is the theta is 0. Cosine of 0 is 1. So we can just say this is equal to 1. And so this is all we need to do. The force will be equal to the work done divided by the displacement. So divided by 0.75 equals, and you get, if you round off to three significant figure, you get 2,610 newtons. Or some it rounds off. It all depends on how you round it off. All right. Any questions on part D? Now part E, if the displacement is 0.015, it's shot into metal, so we can draw a picture of that. Here's some chunk of metal, and the bullet hits and embeds itself, into that metal. It's probably all smushed when it hits, and that displacement is to the right at 0.015 meters. So that's from here to here. Now, we know that the work done by the force stopping the metal is going to be equal to the change in kinetic energy. And this change in kinetic energy is K final minus K initial. Well, we know what K final is. What's the final kinetic energy of the bullet? Well, it stops, so it's 0. And what is this? This is the initial kinetic energy of the bullet, which we got from part B. And that's going to be equal to the force times the displacement. And so you can say the force then is equal to negative K initial over delta X. So this is negative 1,960 joules divided by delta X is 0.015, and you get a pretty big number. I'll just write it as this 131,000 newtons. But it's negative. What does the negative mean? I'm talking about a force. It's to the left, or in the opposite direction that it hit. So there's your answer for that. And you'd expect this force to be huge, right? I mean, when a bullet hits something, it applies very big force. Not for very much time, but it's a big force. And here's the whole problem on screen here. Any questions? Okay, that is all.